Hello students, welcome to another session of All Fours e-learning program. Now in this session we shall take up the applications of Gauss law. Using Gauss law we will derive the electric field due to various charge distributions. So today's topic is electric field due to a point charge using Gauss law. We will derive the electric field due to a point charge using Gauss law. Applying Gauss law, we will derive the formula for the electric field due to point charge. But before going to this, let's have a review. Let's recall what the things we have studied till date. So I was telling you, charge, fundamental property, charge exhibits field around it, right? Every charge shows its interaction with the other charges within its vicinity, the field there. So the space around the charge where the effect of the charge is experienced, you feel the presence of the charge, that space is electric field. And every field has got its own characteristic property called electric field intensity. Now electric field intensity is defined as the electric force experienced per unit positive charge, test charge. Right, the electric field intensity, force experienced, it is electrostatic force. The Coulomb force, Coulomb's law we have studied, force proportional to Q1 Q2 by R square. So F is equal to K Q1 Q2 by R square. K is Coulomb's constant. So that force, Coulomb's law applied to the charge, then we will get electric field. Field is the force experienced per unit test charge. Now there is another term by which you express the strength of the field, that is electric flux. So flux, I was telling you, flux means flow. In Latin, flux means flow. So electric flux, the charge exhibits field around it where the lines of force are produced. The measure of number of lines of force, the count, the measure of number of lines of force passing through a particular space. Now that count is called as electric flux. So flux is given as phi flux. Electric field intensity is also given by another, it's also termed by another thing called electric flux density. Flux is the measure of number of lines of force over a particular space. Now flux density, electric flux density E, it is flux per unit area, phi by A. So implies phi is equal to E dot A, it's EA cos theta. This is electric flux, the measure of the number of lines of force, right? So regarding this electric flux, Gauss has stated a law, a very important law, a vital thing to derive the electric field intensity due to many different charge distributions. Gauss has stated a law called Gauss Law, where he states it as the total electric flux coming out of pertaining to a Gaussian surface over an enclosed surface, the total flux from a Gaussian surface, enclosed surface, is directly proportional to the charge that is enclosed inside the Gaussian surface, the charge that is enclosed inside. So the net flux, the total flux, is directly proportional to charge net, or if I remove the proportionality I get epsilon naught. So Gauss law can also be stated as it is 1 by epsilon naught times the charge that is enclosed inside the Gaussian surface. The total flux is 1 by epsilon naught times the charge that is enclosed inside the Gaussian surface, right? So therefore the flux is determined like this by Gauss law. You know, Gauss law is an alternative to Coulomb's law. It is same as equivalent to a Coulomb's law, but Coulomb's law has a restriction. Coulomb's law is applicable only to point-sized bodies, point-sized stationary bodies, where you can find the force between the interaction between the point charges. But if the same charge is distributed on a line, linear charge on a line of charge, linear charge distribution along one dimension. Now for such things you cannot apply Coulomb law. Charge due to a disk, when charge is distributed in a plane sheet, uniformly charge distributed on a plane sheet, for such things we cannot apply Coulomb's law. For all such continuous charge distribution, to find the electric field we apply Gauss law. Gauss law is useful to evaluate the relation for the electric field due to symmetric charge distributions. It is useful to find the electric field intensity produced by different charge distribution, but mind you that the charge distribution should be symmetric, right? That is one thing. Second, it is also useful to find out the flux emerging from a surface. It is useful to determine the flux from a Gaussian surface. Third, if you know the field, it is also useful to determine the charge distribution on the conducting bodies. So if you know the charge, you can find the electric field intensity. If you know the electric field intensity, you can find the charge distribution. So that way Gauss law is helpful. Right. So applying Gauss law using Gauss law, we shall determine the electric field strength due to a point charge. Now before going to this, we should understand now how this law is applied. How do you apply it to determine the things? There are some rules to be followed. There are some steps to be followed applying which we determine the electric field strength due to different charge distribution. Now, whenever you need to apply Gauss law, first step, you have to imagine a Gaussian surface. Now, what is a Gaussian surface? An imaginary enclosed surface, a hypothetical surface. It need not be a physical surface or a surface of a conducting body or any physical body. It is an imaginary surface, a hypothetical surface, right, imagined around the charge distribution, right? The shape of the Gaussian surface should be symmetric to the charge for whom you are finding the electric field, right? So first step, imagine a Gaussian surface. A Gaussian surface is an imaginary surface enclosing the charge symmetrical to the charged body, an hypothetical surface. First one. Second, Gaussian surface should be imagined such that the surface passes through the point where you are determining the electric field intensity. You are asked to find the electric field intensity at a point P. Let's say you are asked to find the electric field intensity at point P. Then imagine the Gaussian surface such that it passes through the point P, touching this point P like this. Always the Gaussian surface should pass through the point where the electric field strength is to be determined. Second rule. Third, the Gaussian surface that is imagined should be symmetric to the shape of the charged body. Usually a Gaussian surface can be imagined of any shape. It can be of any pattern. But with respect to, according to the charge that is being given to whom you are finding the electric field, symmetrical to the charged body, we have to imagine the Gaussian surface. So normally you consider the Gaussian surface of spherical shape, cylindrical shape, a cuboid, right, so on and so forth. But Gaussian surface, there is no restriction that it should be only of regular shape. It can be of any shape. But while determining the electric field intensity, you should consider a regular, particular, uniformly shaped Gaussian surface, spherical, cylindrical, cuboid or cube shape, so on and so forth. Next, Gaussian surface should be imagined such that Gaussian surface should never pass through the point charge, discrete isolated point charge. Suppose there is a point charge Q, you should never imagine a Gaussian surface passing through the discrete point charge, right? However, you can imagine the Gaussian surface passing through continuous charge distribution. For example, there is a continuous charge distribution of sphere, a spherical charge distribution. You can imagine a Gaussian surface inside the thing, parting the continuous charge distribution. It should never be determined such that it passes through the isolated point charge. But you can imagine the Gaussian surface such that it passes through the continuous charge distribution. You can imagine of this in this case. For continuous charge distribution, charge can pass through the charge that is being distributed. But for point charge, the Gaussian surface should never pass through the discrete point charge. Next, Gaussian surface is to be imagined around the charge distribution such that the direction of the electric field strength is either normal to the Gaussian surface or tangential to the Gaussian surface. The charge, according to the charge distribution, you determine the direction of the electric field intensity. Then imagine the Gaussian surface such that at any point on the surface, the electric field intensity has a direction either normal to the surface or tangential to the surface. This is another restriction that is to be followed, right? So this way, following these restriction rules, you should imagine a Gaussian surface, then passing through the point, then find out the electric field intensity at that point. So coming to this point charge, right? Consider a point charge small q. I am asked to find out the electric field strength due to this point charge at a distance r, let's say at a point P. At a point P. So I have to determine the electric field intensity due to a point charge, right? Using Gauss law, of course. We have determined this by using Coulomb's law. Coulomb's law is restricted only to point charge. But Gauss law, you can apply Gauss law to apply. Gauss law can be applied to find the electric field intensity due to point charge, linear charge, cylindrical charge distribution, spherical charge, a sphere, hollow sphere, spherical shell, solid sphere, charge distributed within the thing, right? So for all such distributions, you can determine the for a plane sheet, disk, charged plane sheet, infinite plane sheet, like this, for anything. So we shall take up the rules. So first of all, we shall find out the electric field due to a point charge. So consider a point charge Q. Let there be a point P at a distance r from it. Now, first step, whenever you are finding the electric field, please follow the steps. First step, imagine a Gaussian surface around this point charge, passing through the point where you are asked to find the electric field. First thing I was telling you, Gaussian surface should always pass through the point where the electric field is to be determined. So passing through the point P where I have to find the electric field, imagine a Gaussian surface. I am imagining a spherical Gaussian surface symmetrical to the point charge. So equidistant from the point charge. And all the points on the Gaussian surface are equidistant. They are at same distance from the point charge. A symmetrical spherical Gaussian surface around the point charge passing through the point P. First point. Second, what will be the direction of the electric field? You know, we have learned while learning the topic electric lines of force. I was telling you, a point charge produces lines of force starting from the charge extending up to infinity radially outward. So the direction of the lines of force are radially outward like this. The lines of force are projected radially outward this way. So the electric field intensity is radially outward. So on the Gaussian surface at any point, you see the direction is normal to the Gaussian surface and radially outward. We have followed the second rule. So I was telling you, the Gaussian surface should be imagined in such a manner that the direction of the electric field intensity should be normally outward to surface, or tangential it should be. So I have imagined it to be normally outward. Second rule is followed. Now, consider a small element, area element ds. A small area element ds. So the electric field intensity here is E and the direction is like this. I am imagining a small area element on the Gaussian surface. Let the area element be ds. I was telling you, whenever you consider a area element, if the surface is of this shape, then the direction of the area is normal to the surface, normal outward normal to the surface. So when I consider the area element like this, on this the direction is outward normal to the surface, right? So the direction of the area element is ds, outward normal, and at that point P, even the electric field is also in the outward normal. So here these two are parallel. If I consider E dot ds, the dot product of E and ds, you know, according to we have learned in first year, dot product A dot B is mod A mod B cos theta, right? So according to that, if I apply, it's mod of the electric field mod of ds cos of the angle between these two. Both are parallel, Parallel in sense theta 0. So it's cos 0. According to trigonometry, cos 0 is 1. So therefore E dot ds bar is simply E ds, equation 1. So the electric field vector and the area vector both are parallel. So the dot product of electric field vector and the area vector E dot ds is E ds, equation 1. Right. Now let us consider the small flux passing through this area element. The small flux emerging through the area element. Let the small flux be d phi. The small flux through the area element, let it be d phi. Let me write the things here. So the small flux through the area element considered at point P, the small flux d phi. But we know, according to the definition of electric flux density is flux per unit area. So flux is E dot ds. The small flux is E dot ds. But we have already determined E dot ds is E ds because the angle is 0, both are parallel. So this becomes E ds, the small flux, where E is the electric field at that point, A ds is the area element there. So the total flux, if I imagine such area elements on this Gaussian surface, like on a spherical surface, if I imagine some tiny patches, each patch a small area element ds, if I imagine all such area elements and integrate the total flux passing through the Gaussian surface, the total flux through the Gaussian surface, it is integral d phi, that is integral E dot ds, integral E ds. So the total flux phi is equal to integral of E ds, right, equation 2. Now, right, coming to the second point. So small flux through the area element d phi is E ds. If I imagine such area elements throughout the surface of the Gaussian surface and the total flux through the area element, the integration of d phi, that is phi is E dot ds. Now coming to the electric field intensity, I have imagined the Gaussian surface symmetrical to the thing. I was telling you the rules while telling the rules of the Gaussian, while considering the Gaussian surface, I was telling you the Gaussian surface should be imagined symmetrically with respect to the charge, such that the electric field state at all the points must remain same. It should be constant, it should be same. So the Gaussian surface is imagined symmetrically at same distance around this point charge. Now the electric field intensity at all the points on this, wherever you consider the area element at any point, the electric field intensity is same. So in this integration, this E term is a constant. It is same at all the points on the Gaussian surface. So therefore this is a constant. So taking the constant out, I get d phi is equal to E integral ds. E is the electric field actually at point P, but because the Gaussian surface is uniformly distributed around the point charge, at all the points the field strength is a constant because it is at equidistant from the charge, and the Gaussian surface is symmetrically considered with respect to the charge. So the value of the electric field strength is a constant. So therefore phi is equal to E integral ds. Now performing the integration, the total surface area of this spherical Gaussian surface, I have imagined a spherical Gaussian surface. So integral ds, in the sense the total surface area of this sphere, if I imagine such area elements throughout the surface, the total surface area integral ds is the surface area of a sphere. We know the surface area of a sphere is 4 pi r square, where r is its radius. So therefore flux we get it as E, the integration of the surface, such area elements if I consider throughout the surface of the sphere, the total area, surface area of the sphere is 4 pi r square. Right, so the total surface area of a sphere, surface area we know, right, surface area is 4 pi r square. Putting this here, I get flux is equal to E into 4 pi r square. Let this be equation 3. Now coming to Gauss law. So I was stating Gauss law in the previous episode. Gauss law is stated as the net flux through a symmetrical Gaussian surface, the total flux through a Gaussian enclosed Gaussian surface is equal to 1 by epsilon naught times the charge that is enclosed inside the Gaussian surface. According to Gauss law, the total flux phi is 1 by epsilon naught times the charge that is enclosed inside, right? So the charge that is enclosed inside is q, right? So therefore, then according to Gauss law, the total flux is q by epsilon naught, that is equation 4, right? According to Gauss law, the flux coming out of a surface, enclosed surface, it is the product of 1 by epsilon naught times the charge that is enclosed inside the Gaussian surface. So flux phi is q inside by epsilon naught. Phi is q by epsilon naught. This is equation 4. Equating 3 and 4 from the equation 3 and 4. So q by epsilon naught is equal to E into 4 pi r square. Equating the equation 3 and 4 there, right? The left hand sides are equal. Equating the right hand sides, I get q by epsilon naught is E into 4 pi r square. Now getting this 4 pi r square down here, I get E is equal to 1 by 4 pi r square q by epsilon naught. It is rewritten as 4 pi epsilon naught q by r square. So this is the electric field intensity due to a point charge. Field intensity due to a point charge at a distance r in its field. So E is 1 by 4 pi epsilon naught q by r square. This is the formula. So this is the way we deduce the electric field intensity using Gauss law. First we consider a area element. First imagine a Gaussian surface. First rule, Gaussian surface should be symmetrical to the point charge, whatever charge that is, charge distribution that is given. So Gaussian, spherical Gaussian surface is imagined around the point charge, right, such that every point is equidistant from the charge. First point. Second, consider a small area element. Area element is ds. Let the electric field at that point be E. Since the Gaussian surface is symmetrical, equidistant from the charge, at all the points on the Gaussian surface, the electric field remains same. So imagine a small area element ds. The small flux through the area element d phi, it is E dot ds. Applying dot product, it is E ds. Now, since the electric field at all the points is same, taking the E value outside, being a constant, I get E integral ds. The surface area of a sphere, I have imagined a spherical Gaussian surface. The total surface area of a sphere is 4 pi r square. So putting it, flux is E into 4 pi r square. According to Gauss law, the flux coming out of an enclosed surface, the flux from a surface is directly proportional to the charge that is enclosed inside. We have considered only one point charge inside Q. So the charge inside is Q by epsilon. Equating both, I get Q is equal to E by 4 pi r square, that is E equal to E into 4 pi r square. Or electric field strength is like, if I write vectorially, now the direction, so the radius vector is the direction outward away from the point charge, it is along the outward normal, radius vector r bar. So the direction, electric field strength is also in the direction of the radius vector. So vectorially, if I represent the electric field, it's 1 by 4 pi epsilon naught q by r square into r cap. R cap is the unit vector. It is the unit vector in the direction of the radius vector. At any point you consider, if I consider the point to be here, this is the radius vector and the electric field intensity is in this direction. So at any point on the Gaussian surface, the electric field and the radius vector both are parallel. So therefore, E, it's 1 by 4 pi epsilon q by r square r cap. Well, r cap we know it is r bar by mod r. Substituting that, you get the vector form. So this way, the electric field is determined using Gauss law. Right? I was telling you, Gauss law is nothing but the other form of Coulomb's law. Even using Coulomb's law, we have determined the electric field intensity due to point charge. Right? In Coulomb's law, we were considering a unit positive test charge at the point P, force between, Coulomb force between them. Applying Coulomb force, we got the same formula. Right? And applying Gauss law, we have obtained the same relation. So Gauss law is nothing but an alternative to Coulomb's law. But Coulomb's law is restricted only to point size bodies. We can apply the same rule, same method to find the electric field intensity for any other type of charge. Any charge distribution you can find out. Mind you that the charge distribution is uniform. Considering a perfect Gaussian surface. You have to imagine a Gaussian surface cleverly. A clever distribution of Gaussian surface should be imagined such that it should be equidistant, symmetrical, and electric field is outward normal at all the points, and the field is same at all the points of the Gaussian surface. Right? If cleverly imagine the Gaussian surface to the charge distribution, you can find the electric field for any uniform charge distribution. Right? So this way we determine the electric field intensity for a point charge. Using a point charge, we can apply for a point charge. Using Gauss law, we can determine the electric field intensity for the point charge like this. Okay, right.